Hey everyone, and welcome. Today, we're going to dive into a really fundamental concept in AP Physics C mechanics called torque. You've probably already got a good gut feeling for what this is. Think about opening a heavy door. Why do you always push on the side with the handle far from the hinges? The answer to all of this lies in understanding torque. So first, let's start off asking the question, what exactly is torque? At its heart, torque, often represented by the Greek letter tau, is the rotational equivalent of force. Just like a net force causes an object to accelerate linearly, a net torque causes an object to have angular acceleration, which means it rotates or changes its rate of rotation. It's essentially a twisting force. Now, the amount of torque you generate doesn't just depend on how hard you push or pull, that's the force F. It also critically depends on where you apply the force relative to some pivot point or axis of motion. That's the distance r. And finally, it depends on the angle theta at which you apply the force. As you can see in this diagram, we have a force F applied at a distance r from the pivot point and some angle theta to that distance vector. This is the pivot point, by the way. So let's quantify torque. We can quantify this with a fundamental equation. The magnitude of torque is given by torque equals Rf sine theta. The units are in Newton meters because it's force times distance, but be very careful. This looks exactly like the units for joules, which is the unit for energy or work. Torque is not an energy. It is a measure of how effectively a force can cause rotation. It is also a vector. So let's break down these variables. Tau is torque, r is the distance from the pit to where the force is applied, F is the magnitude of the applied force, and theta is the angle between R and F. Again, theta is the angle between R and F, when you place them tail to tail. But we should really be talking about sine theta. That's the really important part. It tells us that only the component of force that's perpendicular to the lever arm will actually contribute to the torque. So if you push or pull perfectly perpendicular to r, so theta equals 90, then from your unit circle, you know that sine 90 equals 1, and thus the torque is maximized, as torque will just equal Rf. And this is the most effective way to make something rotate. Conversely, if your force is directed right at the pivot point, or directly away from it, meaning theta equals 0 degrees or 180 degrees, then sine theta equals 0, and there's no torque at all, because torque will be equal to Rf times 0, so regardless of R and F, torque will just be 0. You're not going to make the door rotate by pushing directly into its hinges. See the door hinge right here? If you push right at the hinge, the door won't move at all. So now let's talk about torque's vector quantity and levers. It's really important to remember that torque is also a vector quantity, meaning it has both magnitude and direction. The equation Rf sine theta gives us the magnitude, and the direction tells us about the axis and center of rotation. We find this using the right hand rule. If you curl your fingers of your right hand in the direction that the object would tend to rotate because of the torque, your middle finger points in the direction of the torque itself, which is usually along the axis of rotation. Take a look at the diagram at right. As you notice, the middle finger here is pointing in the direction of the torque vector. But we don't have to worry about this too much because most of the AP test uses 2D problems for torque. We often use a simpler convention for those problems in that counterclockwise torques are considered positive directions and clockwise torques are considered negative direction. The more formal definition is the cross product definition of torque from this equation right here. But let's talk about the lever arm. It's easier to think about torque using the concept of the lever arm, which is often written as R_perp. The lever arm is the perpendicular distance from the axis of rotation directly to the line of action of the force. If you can find this R_perp, then the torque is simply torque equals R_perp F. And mathematically, you'll find out that R_perp is just R sine theta. So torque equals R sine theta times F, meaning it's just the same fundamental idea, just a different way to visualize this. So let's talk about some real world examples, like using a wrench or opening a door. To maximize the torque you apply, you want two things. a large distance r from the pivot point. That's why long wrench handles are better, or why you push a door at its edge. And second, you want to apply your force as perpendicularly as possible to the lever arm, making that sine theta term close to 1. You could also maximize the total force F, but we're assuming F is constant in both cases for this. If you use a short wrench, meaning you have a small R value, you have to apply a much larger force to get the same torque as with a long wrench. If you push a door very close to its hinges with a small R, it's very difficult to get it open. Similarly, if you push the wrench at an odd angle instead of perpendicularly, you're reducing that sine theta factor, which makes your effort less effective at producing torque. Let's take a look at a short video to see torque in action. As you can see, pushing closer to the door barely moves it, and this is because of torque. Since the R value of torque in RF sine theta is small near the door, torque is also small. By moving further from the door, the R value of torque is increased, increasing the torque and thus the movement of the door. But again, this is a review for the AP test, so let's move our focus on problem solving. Primarily, you'll see two types of situations for torque in the AP test. First, static equilibrium problems. An object is in static equilibrium if it's not moving, meaning there's no translational motion, and it must also not be rotating. For this to happen, two conditions absolutely must be met. The net force acting on the object must be zero, meaning F net is zero. And crucially for us today, the net torque acting on the object must also be zero, meaning torque net equals zero. This ensures that there's no angular acceleration. It's not starting to spin or change its rotational state. Think about a balanced seesaw or a stable bridge. We'll talk about rotational dynamics more on the next slide because it's pretty important in most of the torque problems you'll see on the test. So we just talked about situations where torques are balanced, meaning the static equilibrium situation. But what happens when net torque is not zero? It means there's an unbalanced net torque acting on an object, which means it's going to experience an angular acceleration. That means the object's rate of rotation will change. It will speed up its spin, slow down its spin, or change its direction of motion, just like linear acceleration. This fundamental relationship is described by Newton's second law for rotation, which looks a lot like the familiar F equals ma. For rotation, it's net torque equals I alpha. Let's break down those terms. So I is just the moment of inertia. Think about this as the rotational mass on an object. It's a measure of an object's resistance to changes in its rotational motion. Basically said, how hard is it to get it to start spinning, stop spinning, or change its spin? Unlike regular mass, the moment of inertia doesn't just depend on how much stuff there is, but critically, how that mass is distributed relative to the axis of rotation. For example, a solid disk rotating about its center has a moment of inertia I equals 1/2 mr squared, while a hoop of the same mass and radius r, also rotating about its center, has I equals mr squared. The hoop is harder to get spinning because more of its mass is further from the axis, and thus there's a greater torque. And finally, alpha, which is the angular acceleration. This is the rate at which the object's angular velocity is changing. It tells us how quickly the object speeds up or slows down its rotation. The units for angular acceleration are radians per second squared. Oh, I forgot to mention, the units for moment of inertia is kilogram meters squared. So angular acceleration, if you increase angular acceleration, there will be a greater torque. In essence, if you apply net torque to something, it will cause angular acceleration, and the amount of the acceleration will depend inversely on the object's moment of inertia, just like net force causes linear acceleration, which depends inversely on its mass. So let's get into some problem solving. I'll pause first and give you a moment to solve this problem. So this problem is a pretty basic question. So the question reads, suppose a force 40 newtons is applied perpendicularly to the end of a lever that is 0.9 meters long from the pivot. What's the torque produced? Perpendicularly is the key word here. That tells us that the angle theta between R and F is 90 degrees, and we know that sine 90 is equal to 1. So using our equation, torque equals RF sine theta, which is plugged in. And solving this, we get torque equals 36 Newton meters. This is probably the easiest kind of problem on torque you'll ever see on the test, as it is basically just a plug and chug equation. As you'll see with other problems, torque can be a little harder. So the next problem we'll do is a static equilibrium problem. I'll pause and give you a moment to solve this. So we've got this 800 Newton, if you read the question, we have this 800 Newton worker on a 4-meter scaffold. The scaffold itself isn't weightless, it's 500 Newtons, and it's held up by ropes on each end. So here's the question. Where does the worker need to stand? What is the tension in the rope nearest the worker? We need to find that. First things first, let's picture our setup. You can see it on the diagram I'm about to show. But first, we define a few variables. So the weight of the worker is 800 newtons, scaffold's weight's 500, the scaffold length is 4, and the tension in the rope nearest worker is T. The diagram we have is over here. We have our 4-meter long scaffold, has its own weight, which is 500 newtons. Then we have our 800 Newton worker. We're trying to find the tension of the rope nearest the worker, which is over here. So again, in order to maintain static equilibrium, so in order to not have the scaffold and the worker like twisting and turning everywhere, we must have the sum of the torques equal to 0. So let's use the pivot point B as the pivot point. Because again, for torque, there's R value, meaning that we need a pivot point. And then we set the sum of the torque 0, getting this equation. So each of these in the parentheses are just torque values given by R of sine theta. So this is the R value, this is the R value, and this is the F value, it's the F value. And I'll save you the algebra from plugging it in, but if we plug it in and solve, we just get T, the tension, equal to 850 newtons. This is a more typical problem you might see on the AP test, on the multiple choice likely, which means that you should probably aim to solve this kind of problem in about 1 to 2 minutes. The third question we're going to do is on rotational dynamics. Again, I'll pause and give you a moment to solve this. This is probably a problem you would see on an FRQ, as it combines quite a few topics together. So we've got the scenario here, solid cylinder of mass m and radius r. You can see in the diagram how it's suspended. The question is, as the cylinder unrolls and falls, what's its downward acceleration A in terms of g, the acceleration due to gravity? As the cylinder falls, two things are happening. Its center of mass is accelerating downwards, that's linear motion. It's also rotating or unspooling, that's rotational motion. These two are connected by the tape. First, let's draw a free body diagram. This right here is the free body diagram, and there are two main vertical forces acting on the center of mass. Gravity mg pulling it straight down, and tension T from the tape pulling it straight up. The cylinder is accelerating downwards. Let's call that acceleration A. So we can apply Newton's second law, F equals ma, for linear motion. The net force is mg, as you can see, in the direction of A, minus T opposing A. So our first key equation would be mg minus T equals ma. Let's call this equation 1. From this, if we wanted to, we could write T equals mg minus ma. Now let's think about the rotational motion. What's causing the cylinder to rotate? It's the tension from the rope. The tension acts at the rim of the cylinder, a distance r from the axis of rotation, meaning the tension T will create torque. The torque tau is the force times the lever arm distance, which is tau times r. We can use Newton's second law for rotation. T net equals I alpha. We're given I equals 1/2 mr squared over here. So we can plug that into I. And for alpha, remember from angular kinematics that A equals R alpha. That means we can plug in for alpha A over R. Again, torque net is given by RF sine theta. Since sine theta is just 1, then we have the radial distance R times T is this whole equation. So we'll call that equation 2. You'll notice that both equations have T in them. So we can isolate for that T and see if we can find any relationship. So first we have mg minus ma, equation 1 equals 1/2 ma, which you'll get by simplifying equation 2 and dividing by r on both sides. And if you simplify, you'll get that, I'll save you the algebra, a equals 2/3 g. So that's great. But think about it like this. Think about another case. What if it was a ring? Since I equals mr squared for a ring, then a would not be the same as this problem. I encourage you to solve it on your own, but if you do, you'll find that a equals 1/2 g. It is more difficult to accelerate the ring because it has a greater moment of inertia. That's why it has a lower a. So let's talk about lab connections now, a more general overview. It's important to learn about these real-world applications because recent changes to the AP exam, specifically the experimental design on the free response, emphasize this. So a common torque lab would be using a meter stick on a fulcrum. We hang known masses M1, M2 at measured distances, aiming for balance, so no rotation. When balanced, the net torque is 0. This means clockwise torques equal counterclockwise torques, leading to the equation M1G1 was M1GR1 equals M2GR2, which is simplified from torque 1 equals torque 2. This balancing principle is used pretty often in the real world. For example, meteorology labs like the National Institute of Standards and Technology use standard torque calibration machines that operate on this deadweight and lever arm principle to create highly accurate reference torques. So in summary, the recap of absolute essentials is that torque is a twisting force that causes objects to undergo angular acceleration as long as torque net does not equal 0. It is a vector quantity measured in Newton meters, has magnitude and direction. And the two key equations are torque equals RF sine theta and torque equals I alpha. Remember that only the perpendicular component of force creates torque. And for static equilibrium, torque net equals 0 and F net equals 0. Thanks for watching my introduction to torque. If you have any questions, please leave them in the comments below.